Hello, everyone. So I am an automation and control professional who for years focused on the automation system and solutions. Back in the days when we were designing these systems, we did not have to worry about communication or communicating any of the data from the control system to the enterprise layer. This all changed, and it continued to change every day because of Ethernet, because of IoT, because of a lot of trends that are taking place in the industry. So there is a greater need to move the information that exists at the factory floor to the enterprise layer and vice versa. And this need is manifesting itself by the fact that we are going to communicate. We need immediate information sent to the control system from the enterprise, like here's a new request for products, and the control system will adjust. The control system will communicate upward to the enterprise to let the enterprise layers that certain batches are complete, ready to be shipped, all of this. And all of this exchange of data cannot be accomplished by simply having a solid control solution at the factory floor. That is certainly needed, but we're still going to need a lot of infrastructure between the automation solution and the enterprise data layers. And we do this over Ethernet. So therefore, today's session, we are going to present to you some of these communication standards that are governing that space between the factory floor and the enterprise. And what you need to learn as an automation and control specialist to be able to navigate through the systems, to be able to deploy a control system and communicate well to the enterprise and give your end user a complete warranty, so you could assure that data generated at the factory is reachable and is communicated to the right people that need it, inside the factory, outside the factory, anywhere else in the globe. And you know, it's another seminar, but at some point you probably are hearing about IoT, which is Internet of Things, and IIoT, which is Industrial Internet of Things, and a lot of other trends. But it all hinges on the physical infrastructure, on the communication. With this said, I'm going to expose you, if you will, to all of the different consortiums and organizations that existed over the years and evolved the communication standards to what it is today. So IEEE was the originator of the Ethernet standard as we know it, which is the IEC 11801. And a lot of the basic physical communication is based on this standard. So as you see across this table, you will recognize that the Profinet is a subset inside the 1100801 standard. The Ethernet IP is a subset, and so is Modbus TCP. Those are different organizations that generated those subsections, if you will, inside the Ethernet standard. The implementation layer of how these Ethernet need to be implemented in the factory floor is governed by another set of standards that basically is called Industrial Communication Network, and how you lay these networks and field buses in the architecture. So each one of these substandards, if you will, the IEC 61784-2 with subsections, they are talking specifically to how to implement wiring for Profinet over the Ethernet standards that existed in the specifications. As an automation specialist, you do not work in that space generally. What you do most of the time, you are designing a control system that's covered by another set of standards we call ISA. And I will walk you through that in a second. But before we get there, And we need to be cognizant of the fact that we are not living in a bubble. These standards are all existing in different forms depending where you are in the world. So if you look at the top tier of this deck, you will see that the industrial network existed under different set of specs in the office, which what you see on the left, and in the plant floor, what you see on the right. And those standards are slightly different where you are in the enterprise and where you are in the world. So on a worldwide basis, the IEC 11801 is the Ethernet standard that exists for all office architectures. It is different when it comes to the factory floor, and it's known under the IEC 24702, and an ISO global standard is what is implemented worldwide. So you will find elements of this standard in the other standards that exist below. So for instance, in Europe, they use the EN specifications, which are similar to the IEC, but they have different local interpretation for where you are in Europe. Similarly, when you go to the Americas, you will find out that on the office side, all communication networks are governed by the TIA 568 spec. And similarly, on the factory side, the TIA 1005 uses a lot of the elements that exist in the TIA 568, but also include additional requirements for factory type operations, because on the factory, it's a different environment. So therefore, you need to have certain additional guidelines added to strengthen the media, to strengthen the connectivity, to make sure that you've got additional protection for electromagnetics and chemical and dust and other things. Those requirements are different on the plant floor, and therefore the TIA 1005 is the specification that covers all of these extra requirements. So a communication media deployed in the factory system can survive that factory real-time operations, because they are going to be exposed to everything else that an office area you wouldn't find. In an office environment, things are air-conditioned, dust-free, cooled, temperature controlled, and what have you. That is not the case on the factory floor. So therefore, there is a greater emphasis on the part of the specification that it's called MICE. The MICE category, which is the magnetic, ingress, chemical, and electromagnetics, those are additional specs that you find in TIA 1005. So now that you've seen all of these specs, you need, as an automation and control provider, to be cognizant of these specifications when you are deploying your solutions in the Americas, if you're asked to deploy them in Europe, or elsewhere in the world. So you need to look at the subsection and the required spec for those different areas to apply them, to be able to adopt the local differences in your implementation. So with this said, I want to walk you to the next reason why the specifications are different between a factory system and an office system when it comes to communication. So we have two worlds that we have to be aware of. In the past, we used to deal with what's called an IT. An IT organization basically focused on the office environment, and left the factory environment, which what we call the OT environment, to the maintenance technicians, because the Ethernet specifications were not being adopted across the enterprise. That is all changing. So therefore, we need to, and that's converging over time. We are now finding more IT personnel, if you will, being responsible for an OT type environment and vice versa. And as you are looking at those two environments, you need to be aware of some subtle differences in how Ethernet is deployed. So on the office side, we all know you come into your computer every day and you log into it, and you are given an IP address, which we call a dynamic IP address that is assigned by a DHCP server. That is not the case on the plant floor. All the static addresses of IPs are pre-assigned. You already do that today. When you are designing an automation system, you decide beforehand what is the IP address of each one of the controller, each one of the switches, each one of the routers, all of the different I/O substructure. You know how it's communicating to what switch, to what network. All of this is determined and fixed. That is not the case on the office side. And that's a major difference between the two networks. When it comes to the environment, I already mentioned the fact that on the office side, things are air conditioned and controlled. On the plant side, that is not the case. You are dealing with very unique, what we call real life environments. Similarly, when you look at the networks in enterprise, you most likely will find a complete network between all the different offices, because there's one server that's serving up all of the IPs to everyone else. In the factory, you cannot do this, so there is segmentation of these networks, and you find different control system pretty much self-sustained, and in many instances between two adjacent control systems, you might find duplicate IP static addresses. So those could cause major havoc in communications. And similarly, as you go down that list, you will find differences that as a control and automation person, you have to worry about. I will take you to the last one on this list. In an office, when a downtime occurs, it's an inconvenience. You are not able to send email, so you wait a few minutes, let the system clean itself out. That is not possible on the factory side, because the data is continuously being sent back and forth to all the different systems, and sometimes it's a life or death situation. So if a packet that's intended, that's a safety packet moving from one switch to the next, does not make its destination, you could be killing a person. And that's an extreme case, but those are the issues we're dealing with on the factory side. So therefore, communication over the factory systems have to be designed and designed well, and this is where we need to adopt a lot of these standards in those designs. So I take you down one layer. Now here we are as an industrial automation control designer. You are asked all the time to go design a control system, and will most likely be working on the left-hand side of this deck. You are designing, you have an ISA 95 and ISA 88 standard to comply with, to make sure that the automation system has all of these requirements built in for what it needs to do. The minute you are communicating out to any one of the enterprise and to the other work cells for all practical purposes, you are now dealing with communication. And when you do that, there is a next logical step that we need to build in, which is how do we construct the logical network topology? How do we communicate from cell 1 to cell 2 and over what kind of a wire? That type of network and the people that work in that environment have to be certified by an Ethernet body. So for Cisco, for instance, that's one such organization, and they build it over what's called a CPWE, which is a converged plant-wide Ethernet, and it's governed by an ISA 99 spec. So what is converged plant-wide Ethernet? I will talk to you about this in a second. But that is not enough to construct a network. You need to take it to the next step. You need to find out how does the physical network infrastructure put together. And to do so, there are a group of individuals that are trained and need to be educated in that space, and they called RCDD, which are Registered Communication Distribution Designers. These are communication specialists, if you will, that have been certified by a certification body called BICSI, which stands for Building Industry Consulting Services International. And those are people that learn what are the subtleties in running a fiber cable, for how long, how many bend do we have to put on a fiber before we lose communication? If we have copper, how many termination, what are the losses that we expect in connections and so forth, because we are dealing with low voltage communication at this point. And when you're dealing with low voltage communication, you could easily lose the 24 volts like 200 meters down the road, and you will not be able to send the signal. So you need to be aware that the TIA 1005 spec deal with that aspect of how can you get a signal, how can you get a packet, how can you get a communication stream from point A to point B within the factory systems. So then let's take you down one more step to what we call a logical designed network. And this is where the notion of CPWE come in, and it's called the Converged Plant-Wide Ethernet. It's an architecture that's been put together for many, many years by Purdue University, and it defines a framework for the industrial network devices, equipment, and basic network services, how they should work together. So it does not give you the physical, how long is the run between a switch and an I/O, or between an enterprise data center and a lower edge device. It simply tells you they need to communicate, so therefore there is a wire that's been strung between them. And if there is segmentation of the network, it will show you those different segmentation to be able to isolate traffics and so forth. And it's built on the ISO model, the 7 layers in the ISO. So you've got the first 2 layers at the bottoms are where you have a lot of control systems. So this is the layer where you have I/O and control devices and ring networks and star networks and other things. At the layer 2, or in this case the layer 3, because this is 1 and 2, this is 3. At layer 3 is where you are now distributing the communication between different automation control cells, and also defining what type of communication you need to reach the enterprise, what kind of wiring it has to go between the factory system and the enterprise. This architecture also takes in account something we call DMZ, which is the demilitarized zone. Between enterprise systems and factory systems, the designers always found a good reason to segregate and separate these networks. And the way they did it is by simply adding this demilitarized zone devices that basically stop certain traffic from reaching the enterprise layer, either because it's not needed or because it simply could jam the network at the enterprise. It's simply the way they separate the different architectures. So that's logically how an architecture of a control system is placed within the enterprise communication architecture. So now, at every point in these architecture, you find that there are certain type of devices and certain type of communication engines have to be put in place. So for instance, at the wide area network, within the enterprise, you find a lot of control rooms. And control rooms are air conditioned. You've got a lot of servers communicating data and so forth. And this is where the office environment is using the dynamic DHCP IP addressing and everything else. Those types of devices are sold by Panduit and many other companies out there, and they are unique to data centers, unique to ERP systems and all kind of network services and so forth. As you go down to the factory, you are dealing with similar type of systems at the what we call micro data center level. This is in space in the architecture where all the data transacted from the enterprise that need to reach the factory has to go through a data center that's uniquely designed for the factory systems. And this is where you find a lot of different SCADA systems and MRP systems running and so forth in these micro data centers, because this is where you're storing immediate data that's coming up from the control system. And at the same layer, you find something called industrial distribution frames. This is where you're segregating the communication, where you are making sure to separate the copper from the fiber. So within the control system and automation system, you most likely are running copper wires to all of these devices. When you are now starting to run longer systems and longer communication, this is where you start converting a lot of the media from copper to fiber, and you'll find a lot of what we call horizontal fiber runs that are found in the architecture. But at this level, we're only talking logical. We're only saying this is what you're going to need. We're not telling you how long is the run, what type of termination, none of this, just logical how it's running. And at the control, when you get to the automation, you will find different things also. So you find network zones within the architecture, you find control system, cabinets, and so forth. And those are where a lot of the communication network terminates at the edge layers. At this point, I think we're going to stop for a poll. So take a few minutes and answer those questions. It will be helpful to know your input.
Okay, Michael, I'm going to go ahead and close the poll now.
Okay, thank you. So far, we talked to you about the logical architecture and how it's viewed by the network designer that's been versed in how Ethernet network should be communicating. The next topic now is where we need to take all of this information and translate it into what we call a physical. So a logical design basically tells you what type of communication and media have to be strung between 2 points, but it does not tell you what is the status of the network in the real world. So we have to consider distances between those two or two nodes or many of these devices. We have to consider what I explained earlier as the environmental conditions that we have to deal with. And this is where the M.C.E, again, mechanical, ingress, chemical, and electromagnetic type environments have to be considered to find out what type of media we need to run between those systems. And when we need to really worry about what we call, what's something called structured cabling, because if you want to connect point A to point B, and point B happens to be 200 meters away, would you string one wire to those 2 points? Or would you find a methodology where you could find all the network that's going from a group of point A to point B and just put one wire down? And this is where you need to really worry about the physical. And also, you need to understand what type of switch topology you need to put in, and what type of zones you have to create and separate. And this is where the RCDD is very hard at work, because now he has or she has to take the information that's shown in a logical design and be able to look at the premises where the design is going to be, look at the architecture of the building, look at where the poles are, where the power systems are, where the chemicals are going to be, where the vibration, where the power systems, and they have to then worry about, now what do I need to do? How can I put all of these wiring in, keep it safe to make sure it runs, and it runs for a long time. It is expected that when a wire is put in a factory system, it's meant to be there for a good long time. A factory doesn't always go in and replace a wire because they need to add another communication. That used to be the case in the past. That is no longer the case going forward. You need to design it in so it has robustness built into it. So if you want to add another wire, you don't go back to the main drawing board, but you look at what does the architecture allow me to add and where. So that's why it is important to start looking at what type of distribution systems of switches have to be, what kind of operating systems for the communication, are they all at the same level? Do I have information on the bill of material that I need to put together? What kind of information I have from the logical team about how many network schematics do I need? Am I going to need a ring? And if so, where the wiring has to be put in? What ductwork I have to choose? All of these things. So these are deliverables that the logical team have to give to the physical designer to now be able to put it all together. So with this, here are some of the deliverables that usually take place. So you've got the logical architecture on the left-hand side, and this is where you are showing all of the different devices that have to communicate, but you're not telling how and for what type of a wiring. As you study the premises, as you decide what type of hardware has to be installed and how far is it from the main system, then you will start determining, do I run a fiber between those two devices, or do I run copper? Is the distance between them over a certain limitation where communication cannot be secured, and fiber isn't the right answer? What type of copper have to be put in? What type of cabinet I have to choose? Do I have to go choose stainless steel, or do I have to use fiber type of product, or just simply carbon? And at the end, the RCDD, the designer of this network, will put together a physical design that basically has in it all of the buildable components. So you will see here all of the different devices that have to be deployed at some point in this architecture, and where they need to be on the design. If they need to be at the micro data center level, do they need to be near the control, and where? And you find all of these different devices that come up. Is it an industrial distribution frame? Is it a control center, and so forth? And when you go to the physical design, now you have what we call a constructible type documentation that have to be delivered back. And if you happen to be the contractor of record, the person that's responsible for the overall design, you've designed your control system, you asked a subcontractor to look at the communication and deploy it for you, but as a contractor, you are responsible for the whole thing. So you need a certain deliverables back to you, which you then have to turn back into the end user that has physical infrastructure. If you want to program manage the thing, you need to find out, how am I going to deploy it, what it's going to take, all of the different material, the bill of material, all of the networks, when it's at 24 volt, have to be grounded properly. What do I need to do? Where do I ground it? A lot of details that TIA 1005 will take care of, but an RCDD will implement. And as a control and design professional, you could be all of this. You could have different teams doing it, or you could be doing it yourself. The important part is that it gets done right, because if you don't find all of the different pitfalls, if you will, in these specs, you'll end up with a system that's not going to survive a good length of time. So now it comes the part where you have a physical architecture, and the next step is to deploy it. And deploying it will take you to another layer, as RCDDs have to now take the physical design and use what we call a certified technicians that know how to run the fiber, how to terminate it, how to make sure that you've got acceptable losses in the architecture, to ensure that the installation is done with the design specification in mind. So if the logical said, okay, the enterprise device is like 300 meters away from the control system, what do you need to run? Copper is out of the question, so you put fiber, but fiber has limitation on how long, and if it's a single mode, multi-mode, all of this stuff. As a physical designer, the RCDD decided what type of media. The deployment team have now to make sure that they comply with those specifications. So they kick off the project, and in the implementation phase, you need to oversee all of this design deployment. So make sure that you have some planned visits for when certain milestones are being met, and not the end milestone, but we're talking about running the fibers and testing that the fiber is passing that it's not kinked somewhere, that the communication isn't going to make it. When you're running the copper, you have to make sure, are my communication losses still acceptable? When you start connecting the control system, now that's where you come in and start testing your program. But it's before that, you are doing all of these different visit steps to make sure that the architecture that you designed in is continuing to be implemented correctly. So now it takes us to the notion of how can you make sure that a certain design is implemented correctly. And this is where you have to design in what we call the quality testing system. You have to define, if you will, what would be the recommended losses that are acceptable to my system, how long, what type of testing guidelines I need, what type of testing reports I require. And all of this is needed because a lot of the end users, if you will, are looking at this as an IT implementation. In the IT world, when you're running all of this communications, they have to comply to a certain test guidelines. And similarly, when it comes to the manufacturing, all of these specifications translate. So you see here a small subsection of a document that talks to the what type of fiber, what type of nanometer frequencies of communications and so forth. You as an automation designer, you don't have to worry about this. An RCDD communication specialist has to worry about them because they have to make sure that the communication passes. And similarly, when you're doing the viability testing, so you've got all of your test results, you now have to have a set of guidelines, if you will, that says, look, I designed a system, I tested it, I know it passes the limits for my communication. I know that the media chosen abide by a TIA 1005 specs and all of the MICE categorization for what type of cables, what type of connectors. Do I need a decode connector? Do I need just a straight through RJ45? All of that. And basically, you've got complete documentation that says I've got a complete system put together that is now survivable and it's going to make it for a certain number of years. In Panduit, when a logical design is implemented correctly by an RCDD, following all of the guidelines for testing and certification and so forth, at the end, when a person submits all of these test results, the company, Panduit, will issue a warranty that covers this infrastructure for 25 years. And this is important to the end user because the end user doesn't have to worry about the wires in the wall. Back in the days, a lot of the wires used to be in the walls and gone missing for many, many years, but they continue to communicate. Why? Because they over-specified a lot of this hardware. Over-specifying means spending more money for a cable that may or may not need that over-specifications. Doing the right things in these system implementations will assure you that a certain cable is put in place at the right cost point to give you the right protection for all these many years. With this, I think we are going to take another poll. So, Jane, please.
We do have 2 poll questions at this time, so I'm going to give a few moments for the first question here, and then I will move on to the second question. Okay, I just went ahead and posted the second question. Okay, Michael, I'm going to go ahead and close the poll.
Okay, thank you. So we realize that this seminar is going to give you a flavor of what you are expecting in the new world of deploying an automation system in an enterprise or in a factory. The need to communicate to all the other systems within this environment. As an automation and control professional, you may decide that you want to be just simply in this world and not worry about the communication piece. But you need to find the right partner to help you get the communication out to the right systems. Panduit is that right partner. We have a lot of different components and cabling to do that. And there is an army of certified companies that are partners of Panduit that can deliver on a certified communication network between the control system and the rest. If you do decide that your company can take on the communication platform, there are these resources that you could go look at and start educating yourself on this. And also seek out additional recruit, if you will, bring in an RCDD professionals on your staff to be able to handle the communication. And at that time, when you are ready, you want to say, okay, it looks like I'm going to take on a complete system. I'm going to be able to also design and deploy a network, a communication network between the automation system and the rest of my enterprise. You could then come back and let us know that you are now another company that can take on the automation and the communication and give a complete solution. When you do that, we have a platform you could go on. It's called panduitpartners.com. So you could find it through our navigation systems and then identify yourself as a company that can take on an automation and a communication system and a complete system, and you could join this group. So I just want to thank you again for giving me the time to give you this 30,000-foot flyover, if you will, over what you need and what you expect to see to deploy an automation and a control system in the new enterprise. And with this, I think we could now take your questions. Thank you.
Thank you, Michael. We'll use this time now for questions. I already actually have a couple in my chat window here. Please feel free to go ahead and submit any more in the chat window. First question that I have is, the physical network design is an important piece of a solid foundation for an integrated communication infrastructure. How do I make sure that it's done right?
Well, one thing, you have to make sure that it is being deployed by a group of technicians and professionals that have the right certification to deploy these systems. I mentioned in our presentation today this organization that's called BICSI, BICSI is an organization that makes sure that all technicians that are communication specialty have given the knowledge that they require to be able to deploy, to design, to develop, and to deploy those communication networks and make sure that the networks are placed in and are solid. One quick point there is when a certified technician reach their certification, they receive a certificate called RCDD Professional, and that means that they've already they understand how to design, how to develop, and how to deploy those networks. And that's what you need to do. You need to team up with these individuals or go and get that type of training to be able to make sure that these networks are put in place and stay in place for a good long time. The factory is not a trivial place. You've got a lot of systems and hazards, and you need to worry about this. Jane, do we have another?
We do. I have a question. Can I join Panduit's partner program? And if so, what do I need to do?
Well, if I mentioned earlier that you could be that group of automation designers and control system engineers that have already taken on some automation and control and communication projects. And if that's the case, reach out to your local Panduit sales team or your local automation distributor or any distributor that you work with who happens to be a Panduit authorized. Talk to them, let them know that you're interested in joining the Panduit Partner 1 program. They will direct you to our websites, and they will also work with you to make sure that you have the right credentials, if you will. So they first introduce you to our local sales team. Then, in working with these sales professionals, they will help you acquire new projects and so forth, and register to become a Panduit Partner 1 certified design or installer company. So again, the website is panduit.com, and you could look up the partnering section. I hope that helps. Jane?
We do. I think we have time for one more question. IoT is a hot topic for many of our customers. As a control FI, why should I worry about the networks? Can I just bypass all of this to build an IoT solution that answers my customers' immediate needs?
Well, the short answer is you could always do a solution. And it can be a simple IoT implementation that have a control system sends out its data over whatever network to where you want it to reach. However, in a larger implementation, you have to make sure that you have a good communication infrastructure. And the communication infrastructure is very important to get the data out, because it's not just the one time you're sending the data out. You have to make sure that this data continue to go out over so many years. So therefore, a lot of IoT implementations insist that you need to have a good network infrastructure in place. And you need to make sure that all of the different systems that you use for IoT, and by the way, Panduit does have some IoT hardware that takes data from a motor, from a heating, cooling system, from all kind of power systems, and give all of this data over to the enterprise layer, because that's what IoT is. You're using the data outside of its original environment, the original environment being the factory. So the network is the most important part in all of this. You have to have a good network, and it has to be viable for a good long time. So that's why simply implementing an IoT and walking away might serve the purpose just for this one incident, but it will fall short over the long run. So, Jane, do we have any more I could answer in the time remaining?
Looks like we have one more. Is there any standards on how to create a physical diagram of the network, or is that just willy-nilly based on whoever is designing the network?
Well, I mentioned the CPWE. This is a network converged plant-wide Ethernet. It's a specification that's been put forth by Purdue University. You could go look at that. It is the best architecture to be able to segregate all the different devices in the factory and the enterprise. If you do, in the old days, we used to use what it's called point-to-point communication. And it means that if an I/O needs to deliver a turn on, turn off type message, all you need is to string a wire from the I/O to the PLC. And that sufficed for a very good long time. Today, the I/O device isn't just simply sending its data to the PLC. It might also be required in a different cell somewhere else in the building. It may be a safety system that is being monitored by another team somewhere else. And if that's the case, you no longer are sending it to the local PLC, but the PLC has to take it to the next level. And when you do that, you can't just run a wire and run another wire. And if you keep running wires, here's something we tell our installers and designers to do. When they're asked to go into a factory system to assess the network situation, we say to them, just walk around, see what type of wiring they have. So if you walk into a factory that was not designed per a certain structural architectural guideline for separated networks, you will find a bunch of wire just all in one place. It's a big mess. In many cases, you can't identify which wire is live, which one is dead, which one is no longer being used, all of that stuff. And if that's the case, that is a gold mine for someone like you, because you walked in and you said, oh my God, how are you running? You could simply make a case for them that you've got a big problem on hand and you have to worry about this. As a control engineer, you have to make sure that what you build and leave behind continue to run and communicate for a good long time. So how can you make sure that happens if you don't have a solid infrastructure? That is very simple.
Okay. Thank you so much, Michael. I'm going to go ahead and conclude the call because we're at 2 o'clock now. Okay. Thank you for all of your questions and your time today to everyone. This concludes today's webinar. Thank you so much, and you have a great day.